Swayam Prabha. Digital India. Educated India.
Okay, so in this class we will continue with our discussions on longitudinal static stick fixed stability of aircraft. So, as we discussed, for an airplane to have stability in pitch and also to be able to fly at positive angles of attack, it should satisfy two conditions, or rather it should have two properties, right, and they are Cm naught, which has to be positive, and Cm alpha must be negative, right. So, we want to put it graphically. This is how the curve for the whole airplane should look like. Right, this quantity is Cm naught. In the last class, we looked at what is the for a conventional airplane where wing airfoil is supposed to have positive camber for higher lift, and for the CG to be located behind the aerodynamic center of the wing. We saw in the last class that the graph of the wing alone contribution, right, wing alone Cm versus alpha curve looks something like this, right. So, for positive cambered airfoil for the wing gives you this Cm naught, which is negative, right, and Cm alpha is having a positive slope, right. And this is what is desired, right. This is what you get from the wing alone contribution, and this is what is desired for the airplane. Okay. Horizontal tail is actually used on the airplane to change this curve to this, right. So, it is actually used to augment Cm naught, okay, and Cm alpha, right. So, that this is preserved, right. So, you should have the aircraft designed in such a fashion, so that you should have Cm naught which is positive and Cm alpha must be negative, right. So, in the last class we saw that actually wing alone is not enough to satisfy both these criteria, right. So, for this reason what we do is, what is done is a tail is added, a horizontal tail is added to the aircraft behind the wing, okay, so that you can meet this criteria. So today we are going to see or discuss tail contribution. And I can also put H here in front of this, so that it's horizontal tail. Okay. Okay, I'll move. Right. So let's say this is our fuselage reference line. The wing is located here, and relative wind is coming onto the aircraft at an angle of attack which is measured with respect to the fuselage reference line, and therefore it's called alpha FRL, right. So this is your V, relative wind, and this wing is at some incidence angle IW with respect to the fuselage reference line. So total angle of attack at the wing is alpha W right. Now we assume that all the forces, aerodynamic forces, are being shifted to the aerodynamic center of this wing, okay, with a moment, right. So for positively cambered wing, we should have Cm naught, which is negative, right. Okay, this we have seen in the last class, so I will not go on describing this completely in this class. We will focus on what is happening at the tail, right. So tail will also tail is also like wing, smaller wing, right, and is inclined at an angle IT to the fuselage reference line, right, and CG is located somewhere here, right, CG of the aircraft. This is aerodynamic center of the wing, this point, okay, and aerodynamic center of the, so they are both located at quarter chord location, right. And remember we said we are going to measure all the distances from the wing leading edge, right. We are going to measure all the distances from this point, okay. So this is right. All right. So, this part actually we have covered in the last lecture. We are going to focus on the tail now. I just said because of the tail location which is in the wake of the wing, right, we have to account for what is called the downwash angle, right, and that is because of the tip and the leading edge trailing edge vortices at the wing, right. That is going to cause a change in angle of attack of the fuselage reference line at the tail, right, and associated with a change in velocity, right. So, this, if I draw a parallel to that velocity, is something like this, and let us say this is alpha FRL at the wing, okay, and here we are going to see a change in velocity which is smaller than this velocity vector, right, and this angle is the angle of downwash. Okay, so this is the original relative wind speed, and this vector is V prime, right. So, dynamic pressure at the tail is going to change because of this downwash angle, and angle of attack is also changing, right. So, let us assume that the aerodynamic center of the tail is located at a distance LT after the center of gravity, right, and this is the lift created at the tail and the drag, okay, dt. All right. Now, if I want to find out what is the total lift coefficient of this wing plus tail configuration, then you have to add the two lift contributions, right, L lift coming from the wing and the lift coming from the tail, right. Right. So, we want to look at the lift coefficient of the complete airplane. So, this is how you write the lift, which is half rho v squared S into CL. This S is a reference area which is taken as equal to the area of the wing, right. So, this is wing planform area, and this V is the velocity which the wing is seeing, okay, and rho is the density at sea level condition or any other condition, right. It is going to change with height. Now I am adding a CLW here. Okay. These quantities are going to be same, but I am adding a CLW here because I am not using the tail to produce a lift, right. Tail is being used to change Cm naught and Cm alpha, right. That is the only objective why we are using the tail, for stability and control purposes, not to produce lift. But of course, this is the lift which is going to change this profile, right, but only for that reason, not for actually changing the lift of the total aircraft, right. So lift of the wing is just sufficient for taking care of the weight, right. All right. So you can divide the right side by this quantity, so you get okay. So you can also write this as SW because wing platform area is the one which I am using as a reference area, right. What is this quantity? This is the ratio of two dynamic pressures, right. Okay. Ratio of the dynamic pressures Qt over Qw is also known as tail efficiency. Okay. Okay. So this CL is now modified to right. Okay. The value of this quantity lies between 0.8 and 1.2, right. So when do you think it will be 0.8 and when do you think it's 1.2? is pointed when the tail is lying behind the wing, right, in the wake of the wing. If this tail is lying in front of the wing, then this quantity is greater than 1. Okay. So, Qt is less than Qw, right. Okay, you will not call it a tail, right, in that case. It's being called tail because it's lying behind the wing, right. What do you call this surface when it's lying ahead of the wing? It's canard, right. So, for canard configuration, you have Qt which is larger than Qw. Right, and it's mainly because you are seeing an upwash in front of the wing, right, ahead of the wing, and a downwash behind the wing. So, the flow field around the wing will look something like this. Right. So, this is downwash, this is upwash. All right. How is angle of attack going to change at the tail now because of this downwash? So, alpha FRL at the tail is going to be at the wing minus this angle, right. And I have said that we are going to treat this angle of attack, okay, as the angle of attack of the aircraft, right. So, we are going to drop this FRL and write this as alpha. Okay. So, here also this is nothing but alpha plus IW. Okay. So, what is the effective angle of attack at the tail? What is that? Alpha minus epsilon plus IT, right? So I am going to write this as alpha t, okay, at the tail, and that is it can be also written as so this alpha is alpha w minus I w, right. Okay. Now the question is, how do you quantify this angle, right? Of course, for everything in this course, we will assume some empirical relation, okay. But so you have to measure the quantity and just plot it, right. So that is the empirical relation, but there have been some work on this, okay, to quantify this epsilon analytically also, okay. So there the finite wing theory gives you an expression for this epsilon, which is CLW, lift coefficient of the wing, over pi into aspect ratio of the wing, okay. Yeah, okay, so this is 2 into CLW over okay. Yeah, it depends on lot of factors, okay, like where this tail is located behind the wing, right, and how much above, how much below, how close, right, all that is going to affect this angle, okay. But for this course we will assume that this relation is correct, okay. That is something you have to go back and find out from aerodynamics book, right. I will also in this course itself, okay, after a couple of lectures I will give you empirical relation, okay. So I will give you this plot of epsilon against some parameter of the aircraft, right, and then it will be much clear, right. So you will know what this epsilon is, right, when it is lying at a particular distance from the wing, right. So that kind of plot is available, but for now we will keep this, okay. This epsilon is also a function of angle of attack. So you can write this as epsilon equal to epsilon naught at 0 angle of attack, okay, plus 0 angle of attack of the wing, okay. Right. So you can further expand this, right. So there is going to be another term here, which is this, right, okay. Any questions so far? What is our objective? We want to find out, yeah.
Approximation of d epsilon by d alpha and alpha w. is valid only for small, very small alpha W.
Actually, the angle of attack that we are talking about is all in the pre-stall region. Okay, so let us say up to 14-15 degrees.
But it should be delta alpha, right, with respect to some alpha.
It should be delta.
Is epsilon 0 and alpha is 0?
When alpha is 0, epsilon is epsilon naught. Okay, what is our objective? Our objective is to find out the moment of the forces at the tail about the CG of the aircraft, right. So, we want to find out an expression for m CG, right, of the tail. So, what is that going to be? What is this angle? Alpha minus epsilon, right. And this alpha is alpha FRL at the wing. Okay. So, that is what I have taken as angle of attack. So, you have dropped this FRL and then you are taking this angle as alpha. Okay, now let us try to write this expression. What is it? The cos component of this LT multiplied by this distance, right, and the direction of the moment is negative, right. So, minus LT plus and this is going to give a positive moment, right. That is why I have written this plus in front of LT. So, I have to define a distance now. Okay. So, let us say this distance is right, the height of CG above the aerodynamic center of the tail is ZCG. So, this is AC tail. What about other components? Plus or minus? Minus. Right, plus this residual moment. What is the value of this moment for the tail? It will depend what kind of airfoil we have, right, shape of the airfoil at the tail, which is normally symmetric, right. So, this quantity is actually 0 because Okay, now let us try to simplify this. Okay. So, you can assume that the lift at the tail is much greater than the drag, right. That is one assumption, and this is how actually you have to design your tail, right. You cannot have an aerodynamic surface which is giving you more drag than the lift. Okay. Let us say this height of the aerodynamics of the center of gravity from the aerodynamic center of the tail is very small. Okay, and angles are small. So, one assumption is this, second is this, and the third one right. So, this cos alpha minus epsilon is 1, right. Now, this quantity is small, right, because I said angles are small and this is small, right. So, both together product of the two small terms will result in even smaller quantity, right. So, we will neglect the smaller terms only because they are much smaller as compared to the quantity which is large. So, large and small, you have to look at the magnitude of that, and that is how we can drop out terms, right. So, this can be dropped because there are two terms which are small, the product of those two terms is going to be further small, right. Here drag is small, this is small, right. So, you can also drop out this term and same case here, right. So, if you use these assumptions, then I can come down to a single term here which is this, right. Okay. Now, let us try to expand this because all I am interested in is the expression for Cm naught and Cm alpha, right. Okay. So, I am going to non-dimensionalize the quantities. So, remember this is the moment about center of gravity due to the forces on the tail, right. But if you talk about the coefficients, right, non-dimensionalized coefficients, then the reference is that you have to take these quantities at the wing, right. So, half rho v squared S W C bar, which is the mean aerodynamic chord of the wing, and Cm Cg tail, right? Is it clear? And that is equal to minus half rho V prime squared, right, lift at the tail. So, we have written the expression for lift at the tail, right, T into the arm length. Okay. So, Cm Cg due to the tail is minus Is this all right?
Why are we using two different reference areas? Like the moment we use SW, the lift we are using SW.
SW is S, okay. So, you can S is the reference area which I am taking as the wing platform area.
For the lift also you should use the same reference area.
For the lift also,
Use the same thing with S.
No. You are talking about this quantity.
Yes, so it comes.
So, how do you calculate lift over any surface? You have to take the area of that particular surface, right?
But why are we using SW for
This I am using only for non-dimensionalizing the quantities. Why not?
We have been using SW so far. We use whatever you consistency uses
If you write the complete expression for the whole airplane, right, this will only come as a component, right. So, when I am writing mCg for the whole airplane and I am trying to find out Cm for the complete airplane, there I am making this assumption that the reference area is the wing platform area. Okay. Right. This VH is called tail volume ratio, right. What do you want to find? You want to find out Cm naught due to tail, right, and Cm alpha due to tail, right. Finally, we have arrived at an expression which is the CmCg due to tail, and that is equal to this, right. Now, this VH is something you can play with when you are designing your aircraft, so that you can have more stability, more Cm naught, and that you can find out by expanding this, right. So, this VH is the ratio of St into Lt. This Lt I can play with, right, St I can play with after you have fixed your wing, isn't it? And you can also play with some more parameters which are coming from here, okay. Remember, everything we are doing here or throughout this course, we are doing it only in the pre-stall region, okay. So, I can write this CLT as CL alpha tail into alpha tail, right. So, lift curve slope at the tail can also be written as this AT, right. Into alpha tail, which is all right. Now, I am going to separate it out in two parts, right. One part is going to give me Cm naught, other part is going to give me Cm alpha, right. Right. So, all these quantities here are fixed, right. So, you can fix your wing incidence with respect to the fuselage reference line, IT tail incidence and this epsilon naught, right. This part is a function of angle of attack, right. Okay. So, Cm naught due to tail is what is that? Minus eta into VH into AT right. So, Cm naught has to be positive, right, and Cm alpha has to be negative, right. Look at these terms here, this is going to be positive, right, this is also positive, left curve slope of the tail is also positive. Yeah, any question?
The second line, D, the next terms.
DCM CG tail,
DCM?
CG tail. Right, d epsilon over d alpha is actually less than 1, okay, much less than 1. So, overall you are going to achieve what you started with, you wanted to add a tail so that you can get Cm alpha curve for the airplane to become negative, right. For the wing alone configuration it was coming out to be positive, the slope, right. And Cm naught is something you can adjust, right. You can choose these angles in such a fashion that you get this Cm naught positive, right. Any question? So total Cm naught for the wing plus tail configuration is Cm naught due to wing plus Cm naught due to tail, right. So and Cm alpha wing plus tail is the sum of these two quantities, right. So we can continue from here in the next lecture.